In problem 2.2.15s, we're going to be finding the present value of a perpetuity-immediate, which is an annuity immediate that goes on forever, perpetually, with payments that are every 4 months and is related to another perpetuity-immediate that has payments every 3 years by a common effective annual interest rate. So this is in keeping with one of the main subjects in section 2.2 where we have these differing compounding periods. All right, so at an effective annual interest rate I, the present value of the first perpetuity that pays 10 at the end of each 3-year period with the first payment at the end of year 6 is 32. So that's the first perpetuity immediate. The same effective annual interest rate is going for the second perpetuity immediate. The present value of this perpetuity immediate that pays 1 at the end of each 4-month period is x, and the goal of the problem is to calculate x. We'll draw our timeline, and I think I will take the numbers to be in years, and maybe have a lot of them because the first payment's not going to start until time 6, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, for good measure there. Not that you have to write all these things, but for good measure, we'll go ahead and write them and see them. So for the first perpetuity, which I'll use in purple, we are paying x starting at the end of year 6, so that would be at time 6. We're paying 10 at the end of year 6, and then every 3 years after that, so at time 9, and at time 12, and at time 15, etc., forever and ever. And for the other perpetuity that I will put in red, and I think I'll make like little X's here, marking every 4 months, 3 times a year. The payment for that one is going to be 1, and also be something that goes on forever. The first perpetuity has a present value at time 0 of 32. What is its present value 1 period before the first payment? Well, that would be the amount, 10, divided by, in this case, what you would call the effective 3-year interest rate, which is not what I is. I is an effective annual interest rate. Let's let J be the effective 3-year interest rate. If that's J, then the present value of this annuity immediate is going to be 10 over J. We already know that from previous videos. I need to get back to time 0, so I need to multiply that by the discount factor, usually written as V, but V in this case would be the same as 1 over 1 plus J, so I can write the present value at time 0 of the annuity in purple as 10 over J times 1 plus J. That's the present value at time 0. That has to equal 32. For the annuity that's in red, every 4 months, we discount it back in time by 1 period, which would be 1 4-month period to get to time 0. If we let K be the effective 4-month interest rate, then the present value of that perpetuity immediate at time 0 would be 1 over K. And that's the quantity that they're calling X. That's the quantity that we want to find. If we could find J from this equation, which we should be able to do with the quadratic formula, and then find some relationship between J, I, and K, then we could ultimately find K and then ultimately find X. And that's the way the problem will go. But what is the relationship between J, I, and K? Since, first of all, K is a 4-month interest rate, so it's compounded 3 times per year, we can say that 1 plus K to the third equals 1 plus I. And since J is a 3-year interest rate, we can also say that 1 plus I to the third equals 1 plus J. We can now use these equations to get K in terms of J. We can take this equation and take the third root of both sides. 1 plus K will be 1 plus I to the 1/3. Likewise, 1 plus I is 1 plus J to the 1/3. Therefore, 1 plus k, if you combine these things, 1 plus k is 1 plus j to the 1/9, right? You'd have, because it's going to be 1 plus j to the 1/3 to the 1/3. And you multiply those exponents, 1/3 times 1/3 is 1/9. Maybe you could see that quicker than I did it. You wouldn't necessarily even have to write this out. To see that 1 plus k is going to be 1 plus j to the 1/9. K is then going to be 1 plus j to the 1/9 minus 1. But we need to find j from this equation. Multiply both sides of that equation by j and also by 1 plus j, and you'll get 32j plus 32j squared equals 10. Dividing everything by 2 and rearranging gives 16j squared plus 16j minus 5 equals 0, which can be factored, but if you're feeling unsure about your factoring skills, you can always use the quadratic formula. J is going to be negative 16 plus or minus, though it would have to be the plus. J has to be positive. Choose the plus. Square root of 16 squared is 256. Minus 4 times 16 times negative 5 is going to be plus 320. All divided by 2 times 16, all divided by 32. This will become negative 0.5 plus, this is square root of 576, which is 24. 24 divided by 32 is 3/4 or 0.75. J is 0.25. All right, so now you go back up here and figure out K. Use my calculator at this point. J is 0.25, so I do 1.25 to the 1/9 power. 1.25. 1/9 is 0.1 repeating, so raise this to the 0.111111 power. Subtract 1, and there's the value of k, 0.0251 approximately. We're after its reciprocal. We're after x. What is the reciprocal? The reciprocal is 39.83, and that is the answer to the problem. Let me just remark that in the solutions manual that goes with the 6th edition of Broverman, they write 39.84. Of course, that's not far away, but I've double-checked this a number of times. It really does round to 39.83 as the correct answer.